Hello everyone. Welcome to the lecture series Foundation for VLSI Design. This is the third lecture. In this lecture, we'll be continuing with the digital system. Specifically, in this lecture, we'll be looking into combinational circuit elements, that is logic gates, multiplexers and demultiplexers, and we'll also look into how to implement a given Boolean function using 2 to 1 multiplexers only. So let us first look into what is a logic gate. So a logic gate has one or more inputs and one output. So the examples of logic gates are basic logic gates like AND, or NOT, right? So these are basic logic gates. So any given Boolean function we can implement using these three basic logic gates, right? So we can implement any given complicated Boolean function by connecting logic gates, these three basic logic gates, and obtaining a logic circuit. For example, if we are given a function y is equal to a plus b bar c, we can implement it using a logic circuit, right? So this is a logic function, and we can implement a given logic function or Boolean function using logic circuit. So this is a logic circuit, right? So it implements this. This is b, this is c, so this is b bar, right? And this is b bar c, right? And then this is OR of a and b bar c, or b complement c. So this logic circuit implements the given Boolean function y is equal to a plus b bar c. Now these logic gates are basically implemented using transistors, resistors, diodes, and so on, right? So and we should understand that uh, three basic logic gates, and, or, and not, those are sufficient to implement any given Boolean function. However, for a given technology, there can be some other logic gates which can be implemented more efficiently. For example, in the CMOS technology that is widely used in the semiconductor industry, the NAND logic gate and NOR logic gates, these can be implemented much more efficiently in terms of delay, power, area, and other figures of merit. So these logic gates like NAND and NOR are very popular. So this is the schematic of a NAND logic gate. This is a NOR gate, right? So these NAND gate and NOR gates are known as universal gates, right? So we should differentiate between the basic logic gates. Basic logic gates are AND gate, OR gate, and NOT gate. And NAND and NOR gates are considered as universal gates. Why they are considered universal gates? Because we can implement any given Boolean function using only say NAND gate, right? So as I stated earlier, that we can implement any given Boolean function in terms of AND, OR, and NOT. And I will just illustrate that using NAND gate, we can implement all these three types of gates, and that is sufficient to show or demonstrate that NAND gate can be used as a universal gate or to implement any logic, right? So let's first see that how NAND gate can be used as an inverter or NOT gate, right? So if we have a NAND gate and we give the same input, right? Suppose the input variable is A, and we provide the same input to the NAND gate, right? A is going to both the inputs of a two input NAND gate. Then what will be this output? This output is A dot A whole complement, and it is nothing but A complement, right? So it implements a NOT gate. AND gate is very easy, right? So we have say A and B. So this is A dot B whole complement, and here if we use an inverter, right? So we get A dot B, right? So this is an inverter because we have provided the same input to this NAND gate. So we get an inverter and implement an inverter. So the output here is A dot B or A and B, right? So we can use NAND gate to implement AND gate. Similarly, we can also see that we can implement a OR gate using a NAND gate. For example, let's see what will be the output of this structure. Sorry, these are all our NAND gates, right? So suppose the input is A and B. So this point, since we are providing the same input to the NAND gate, this point is nothing but A complement, and this point is nothing but B complement. Now what is this Z? We can write Z is equal to A complement dot B complement whole complement. We have just seen that the inputs to this NAND gate are A complement and B complement. Therefore, and this is a NAND gate, so Z will be nothing but A complement dot B complement whole complement. Now we can use the De Morgan's theorem, which we discussed in the first lecture, to expand this, right? So this will become A complement whole complement plus B complement whole complement. And a complement of complement is the same variable, right? So it will be A and this will be B. So we can use two input NAND gate to get a two input NAND gates, right? Three two input NAND gates to implement a two input AND gate, right? So if we want, we can use NAND gate to implement AND gate, OR gate, or NOT gate, all three types of gates, and therefore this NAND gate alone can be used to implement any given Boolean logic function, right? So some other logic gates can be implemented efficiently using transistors, and those are XOR gates and XNOR gates, right? So this is the schematic symbol of an XOR gate, right? And this is a schematic symbol of an XNOR gate, right? So XOR is we can is output Z is A dot B whole complement plus A complement B, right? So we can see that what will be the logic function or the truth table of this XOR gate, right? So whenever the both inputs are, so there are four possibilities. So if we say A and B, so there are four possibilities, right? And what will be the Z is equal to, that is the A XOR. So this is a symbol for XOR. A XOR B will be when both are 0, right? So this will be, both will be 0. So the first one will be 0, the second will be 1, right? And if in this other case, when it is 0, this is 1 and other will be 0. So when A, B both are 0, it will be 0, right? When A is 0 and B is 1, right? A is 0, the B is 1, this term will be 1, right? And therefore Z will be 1. When A is 1 and B is 0, this term will be 1, right? And again, when A and B both are 1, both these terms will be 0 and will get a 0, right? So this is the truth table for an XOR gate. Now let us look into another kind of a logic gate, that is multiplexer, right? So a multiplexer has multiple data inputs, multiple data, right? There will be multiple data pins and multiple select pins, right? There will be data pins, there will be select pins, and only one output, right? A multiplexer will have only one output. So depending on the value of the signals at the select pins, so depending on the values on the select pin, one of the data pins signals is passed, or one of these data pins value will be passed to the output, right? So this is the general functionality of a multiplexer. So now let us look into a simplest type of multiplexer, that is 2 to 1 multiplexer. 2 to 1 multiplexer. So in 2 to 1 multiplexer, we have two input lines or data lines, in 0 and in 1, and we have only one select line S, right? So when S is equal to 0, whenever S takes the value of 0, then whatever the value at in 0 is, that will pass to 1, right? And whenever s is equal to 1, then whatever the value if of in1 is, that will pass to 1, right? So this is the functionality of a 2 to 1 mux. So select line or S line is basically selecting which input will be passing on to the output Y, right? So this is the functionality of a 2 to 1 multiplexer, right? So what will be the Boolean function for Y in terms of inputs, right? So we can see that we can easily write that what will be this functionality. So whenever S is equal to 0, right? So we can write that S bar, then the Y will be equal to S bar into in 0, right? For the case S is equal to 0. And when S is equal to 1, S is equal to 1, then whatever the value is at in 1, that will be passed to Y, right? So this will be the functionality of or the Boolean function or logic function for the Y in terms of input. Y is equal to S naught, sorry, this should be S, it shouldn't be S naught, S into in no, sorry, this will be S bar, it is rather than S naught, it should be S bar. So Y is equal to S bar into dot in 0 plus S into in 1, right? So this is the Boolean function, and we can, using this Boolean function, we can easily implement implement an multiplexer, right? So this one is in 0 into S bar, right? And this one is in 1 into S, and then we are taking the OR of it. Now, the similar to multiplexer, or rather the opposite of multiplexer is de-multiplexer. So in a de-multiplexer has one data input, right? So rather than multiple data input, a de-multiplexer will have only one data input, and there will be multiple in select lines. There will be multiple select lines, and there will be multiple output lines also, right? So depending on the value of the signals at the select pins, so these are select pins, value depending on the value of the signals at the select pins, the data pin signal, this is the data pin, will be passed to one of the outputs. So one of the outputs will get the value of the data, right? So this is data, right, passed to one of the outputs, and the lines which are not receiving the data, that will be that will get a value of 0, that will remain 0. So this is the functionality of a demultiplexer. So let us look into the simplest form of demultiplexer, that is 1 to 2 demultiplexer. So in 1 to 2 demultiplexer, we have one data line, one select line, and two output lines, right? And the functionality is that when S is equal to 0, then Y0 will receive the value of in, right? So whether if the in is 0, then Y0 will be 0. If in is 1, Y0 will be 1, right? When S is equal to 0. When S is and what will be the value of Y1 when S is equal to 0? At that time, in1 will not go to Y1, and Y1 will be simply held to 0. Now, when S is equal to 1, what happens? When S is equal to 1, in that case, Y0 remains at 0, while in data will pass to Y1, right? What it means is that if in1 was 0, then Y1 will get a value of 0. If in1 was 1, Y1 will get a value of 1, right? So whatever the value at in, that will pass to Y1 when S is equal to 1. So this is the functionality, simple functionality of a 1 to 2 demultiplexer. And we can easily write the Boolean function for Y0 and Y1 in terms of inputs, right? So Y0 will be S complement into in, right? Why S complement? Because when S was 0, then Y0 will receive in, right? And when S is 1, then Y1 receives the value of in, and that's why Y1 is equal to S dot in, right? S dot in, or S and in. And using this Boolean function, we can implement the Boolean circuit or logic circuit, or we can implement the demultiplexer. This is a demultiplexer using logic circuit, right? So whenever select is 0, right, this inverter gets a value of 1, and whatever the in1 will be there, it will be selected to Y0. And whenever S is equal to 0, this one will be getting 0 and y1 will be held to 0. And when s is equal to 1, right, so the inverter will produce a value of, whenever s is equal to 1, the inverter will produce a value of 0, and this y0 will become 0. And whenever s is equal to 1, the whatever the in was there, that will pass to the y1, right? So this is implementing the demultiplexer. Now let us look into a simple problem, that how can we implement any given Boolean function using 2 to 1 multiplexers, right? So any given Boolean function. You might have seen this type of problem multiple times. For example, if you may be asked to implement an inverter using 2 to 1 multiplexer, how will you do it, right? So this type of problem is encountered multiple time in logic implementation, and let us understand what would be a generalized solution to this type of problem. For first, let's take a few examples, right? So implementing an inverter using a 2 to 1 multiplexer. So we can implement an inverter simply like this, right? So suppose this was held to 0, this was held to 1, right? And we have, or rather, this one is held to 1 and this one is 0, and this is the 0 select line, this is 1 select line, and we give a Boolean variable a, given variable a, right? So if a was 0, then 0 select line will be selected, and there we have applied a constant value 1, and therefore the output will be a is equal y will be is equal to 1, right? And if a is equal to 1, right, in that case one line is selected, and we'll get, instead of this 0 will pass to the output and y will have a value of 0. So when a is 0, y is 1, a is 1, y is 0, right? So this is an invert, right? This is how we can implement an inverter, right? Similarly, we can implement a 2 input OR gate using 2 to 1 multiplexer. How can we do it? So let's see. So this is a 2 to 1 inverter, right? On the select line, let's apply the variable a. So we are given two input variables, right, a and b, right? And we want to implement a or b, right, using 2 to 1 multiplexer. So let's see how we can do it. So on the select line, we give a, right? Now if the a is 0, a is equal to 0, then whatever will be the b value of b, that will be the output of the AND gate, OR gate, right? So on the 0 select line, we put a variable b. So if b was 0, then the output will be 0, right? If b was 1, the output will be 1, right? That is what the functionality is. And if a is equal to 1, then then the output should be 1, right? So here we can give the constant signal 1, right? So this is the one select line. So this is one data for this multiplexer. So when a is equal to 1, this line will be selected and z will become 1. So this is a very simple implementation of a 2 input OR gate using 2 to 1 multiplexer. Similarly, we can implement an AND gate, right? So instead of, in this case, if we can put 0 on the 0 line, right? So if a is equal to 0, z will be 0, right? Irrespective of the value of b, right? But if a is equal to 1, the output z will be the value of b. For example, if b was 0, then z will be 0. If b was 1, it means that a is also 1 and b is also 1, and in that case, z will become 1, right? So this is an implementation of an AND gate, right? So for simple logic gates like inverter, OR gate, AND gate, it is very easy to find a two input 2 to 1 multiplexer based implementation, right? Now if we ask the question that you are given an arbitrary Boolean function, right? For example, we are asked to implement the Boolean function f is equal to w1 w2 w1 w3 w2 w3. This is an arbitrary, I have just taken an example of an arbitrary Boolean function, and you are asked to implement it using only constant zeros and ones and 2 to 1 multiplexer. How can you do it? Right? So this problem can be solved with the help of what is known as Shanon expansion theorem. So let us look into what is Shanon expansion theorem. This theorem is very, very important for logic circuits, not only in design but also in verification. And therefore, you should be very much thorough in Shanon expansion theorem. So let's look into Shanon expansion theorem. So Shannon expansion theorem basically decomposes a given Boolean function in as a sum of two Boolean functions, right? So suppose we are given any Boolean function f in terms of Boolean variable w1, w2 to wn. So there are n variables, right? So there are n variables w1, w2 to wn, right? So this Boolean function, it can be decomposed as a sum of two Boolean functions by picking any one variable, right? So we pick, without loss of generality, let's pick the first variable w1 as the one based on which we are decomposing this function, right? So given this Boolean function, we are decomposing it into sum of two functions, right? This is the first function, this is the second function. And how do we get these two functions? We get it by setting the value of w1 as 0 in the first case and 1 in the second case. So let's see. So that this term, the first term is when the term f0, w2, w3 to wn is known as the cofactor of f with respect to w1 dash, also known as negative cofactor with respect to w1. So in a given Boolean function, if we put the value of a variable as 0, right? So that variable goes away, right? So this function is independent of w1, right? So if once we do that, then we get a function which is known as a negative cofactor with respect to w1. So it is obtained by replacing all occurrences of w1 in f with 0. And we denote it as f subscript w1 dash. Similarly, what we can do is that we can replace this w1 with 1 everywhere in replacing all occurrences of w1 in f with 1. When we do that, then we get the function f w1, w2, wn. So note that this function is independent of w1, right? And this is known as the cofactor of f with respect to w1, or it is also known as positive cofactor. Why? Because we have taken the value of w1 as 1. Then we get positive cofactor. If we take the value of a variable as 0, then we get a negative cofactor. So we denote the positive cofactor as f subscript w1. So we denote that we denote the negative cofactor as f subscript w1 dash, and we can write the entire Boolean function f as sum of these two functions. This is the negative cofactor, this is the positive cofactor. In this, since we have taken the value of w1 as 0, we write w1 dash or w1 complement, and in this we write as w1, right? So let me explain this with the help of example, then it will be clear that what is Shannon expansion, right? It is very simple thing. We are just representing a function in another form, a Boolean function in another form, right? Now let me illustrate that how we can use the Shannon expansion theorem to decompose a given logic function, and then we use the decomposition to obtain a 2 to 1 multiplexer implementation of a given logic function. So we take a general the logic function that we saw earlier, f is equal to w1 w2 plus w1 w3 plus w2 w3, right? So what we do is that first we expand with respect to the variable w1. The first variable we choose w1, and we find positive cofactor and negative cofactor of this function, right? So what will be the negative cofactor when we expand with respect to w1? So to get the negative cofactor, we have to put the value of w1 0 everywhere in this function, right? So if we do that, this term will go away, this term will go away, and we'll be left with w2 w3, right? So that is the negative cofactor. And to get the positive cofactor, we have to make W1 is equal to 1. So if we do that, then in this term W1 will disappear, in this term W1 will disappear, and we'll be left with W2 plus W3 plus W2 W3, right? So now this is the decomposition of the logic function f, right? So this decomposition, so we have written this function f in another form, right? So the form is f is equal to W1 complement into the negative cofactor, that is W2 W3, plus W1 ANDed with the positive cofactor W2 plus W3 plus W2 W3, right? Now you should verify by drawing truth table. You can verify that this function f and this function are the same function, right? We have just represented it in two different ways or in another way. So Shannon expansion theorem gives another representation of a given Boolean function, and it is in terms of negative cofactor and the positive cofactor, right? So you can verify that this function f is the same as the original f, right? And why we have done this decomposition? We have done this decomposition because now this decomposition allows us to write write a function in terms of a MUX implementation. For example, we can think of a 2-to-1 multiplexer in which there is a select line W1, right? And on the input line we have the function f1 dash, that is the negative cofactor, and on the other, so this is the 0 input, and on the 1 input we have fw, and this is the function. So we have implemented the logic function f using 2-to-1 multiplexer, right? So this f1, this negative cofactor and positive cofactor, those needs to be further expanded or implemented in terms of multiplexer, and we can do that again by applying the Shannon expansion theorem recursively. Now we pick the another variable, that is W2, in these two cofactors, and then we can get another level of the MUX, and if we do it recursively until we get the final variable, only one variable or the constant, then we get a implementation of a Boolean function in terms of 2-to-1 MUX only, right? So now let us say we have represented the logic function f using multiplexer at one level. Now the next level will come. So in next level we choose the next variable, that is W2 for expansion, right? So first we take the negative cofactor and expand it with respect to W2, right? So the negative cofactor is W2 W3. We expand it with respect to W2. So if we make W2 is equal to 0, we get 0. If we make W2 is equal to 1, we get W3. Similarly, we expand the other cofactor with respect to W2. So we'll get, if we make W2 is equal to 0, right? Then this term will get will become 0, and we'll be left with W3. And if we make W2 is equal to 1, this whole cofactor becomes 1, and we get as 1, right? So using this decomposition, we can get the next level of the MUX-tree implementation. And how it will look like? It will look like something like this. So this is the first level that we saw, and this function is nothing but f w1 dash, and this is nothing but, this function is nothing but f w1, right? And then we expanded f w1 dash, right, with respect to W2, right? So we get the first cofactor, negative cofactor here, and other is W3, right? And in the select line again we have W2, and we are getting W3 as a negative cofactor and 1 as the positive cofactor, right? And here on the select line, we have W, right? So given a logic function, we can implement it, given a Boolean logic function, we can implement it using only 2 to 1 multiplexer in a form of a tree, which is shown here. On the select lines, we use that variable that is used for decomposition in Shanon expansion theorem. So this was just one of the just an illustration of the Shanon expansion theorem to understand that how we can represent a given Boolean function in another way, right? But you should note that Shanon expansion theorem is very powerful and it is used widely in VLSI design for many purposes, as you will see in advanced courses. So these are some of the references that I have used in this lecture. So let me summarize what we have done in this lecture. So in this lecture, we have looked into combinational circuit elements. We have looked into basic logic gates. We looked into universal logic gates. We looked into XOR gate, XNOR gate, and we also looked into multiplexer and demultiplexer. Then we looked into Shanon expansion theorem and how Shanon expansion theorem can be used to implement any given Boolean logic function using 2 to 1 muxes. So that's it for this lecture. Thank you very much.